Thank you, John. Yeah, I want to start with a great thank you to all the organizers and especially for John. Great talks we had last few days. So yeah, maybe it's not, if you can see the laser actually. I hope you can. Anyway, I don't know if it's probabilistic numerics explicitly, but I have both ingredients in my works, so I hope you can find it interesting somehow. So I will start with a brief, just a recap about Gaussian process. I know you had that a lot, but still just to keep the notations and give some highlights if I need. So let's start maybe with the most basic model, right? Bayesian linear regression. So you assume you have some Gaussian noise, you have your prior likelihood, and this is the most basic formulation, right? And then you can use the Bayes rule to find the posterior. That's what we do, right? And we can derive all the formulas. And what is more interesting to do is replace this linear function, right, in the most simple model, with something that is not linear. So you actually have a transformation. Let's call it phi of x, okay, multiplied by w. And then you have both your mean, we usually assume it 0, of course, and variance, covariance. And this actually defines you a feature map, what we call it a feature map. And this gives rise to the kernel trick, right, that you can compute using this inner product, but we don't usually want to compute it directly. So that's how I want you to think about that as a function space, okay? And what is interesting here that this reproducing kernel Hilbert space that we work in with for these feature maps, it can be also infinite dimensional, right? So here, for example, I have a very simple example for something that is finite, right? But it doesn't have to be finite. Okay, so I want to consider different families of kernels, okay? It can be anything from this list. What I think is most interesting is the Matern kernel, right? Because you have this parameter nu that captures some smoothness to the function. So personally, I think it's one of the most interesting to look at, because if you capture that one behavior, you can describe many other kernels, right? Okay, and then as we already know, we have the definition of Gaussian process regression. Okay, so we have the mean, which we assume to be 0 most of the time, otherwise you can just do shifting. And we have the covariance, so I assume I know the covariance, okay, this kernel function. And for a given set of points in my data sets, we can define this kernel matrix. So in the definition of Gaussian process regression, I know we already had a talk today that compared between cross-validation and the log likelihood estimation. But I want to focus in this talk more about the maximum log likelihood, which is, to me, the more classical option. And the problem in the whole process, and this is my highlight maybe, the problem is that you need to inverse this kernel matrix, okay? Which is, well, you have a number of cubic computations, which is a lot, right, for large data sets. So this really gives rise to many approximations that can be used in order to maybe find a nice approximation to this and save some of the computations. Okay, so this is, of course, some prior and the posterior after the GP process. I think this book was already mentioned today, but still one of the best books from GPs for machine learning. And another thing that I want to mention before I get more into the details of the model is that when we do this log likelihood maximization, the optimization problem itself, it's not really easy, right? First, you don't have global optimizer point that is guaranteed. And second, already in the formulas for the likelihood itself, again, you have all these expensive computations for the inverse, right? So nothing here is trivial to me as someone who's doing numerical analysis. Okay, so what I want to do is, well, model some approximation for this kernel matrix. Okay, I want actually to approximate the kernel function itself, and of course it will define the matrix approximation. So what we're doing is consider this class of kernels that can be written as an integral form. And you can think about many kernels that can be written in such form, right? And I have this feature map Phi, okay, which we only assume that it's even function according to the feature parameter. So one important example for such kernels are shift invariant kernels. Okay, there are many other names that says that, okay, but basically you can take these kernels and write them as just a function of the difference between the points themselves. And according to Bochner theorem, you can just represent these kernels according to Fourier transform. So this is a, one motivational example to look at the integral representation for kernels. Okay, but in our case, I do not assume that this phi is, exponent. It can be anything. Okay, if there are any questions, of course, feel free to ask. Okay, so.
Sorry, I have a question. What does
yes.
the subindex n mean?
Again, sorry?
In the integral below, what does the subindex n mean?
This one?
Yeah.
Okay, sorry. So, yes, these are some notations. So, sigma f square is the scaling parameter. It's a hyperparameter. And sigma n square is actually just a regularizer parameter. I assume to have some regularization in the process. Okay, it's, well, most of the time maybe you tend to use it as lambda, but it's the same. Okay. Yeah, so what you can do when you have integrals, some kind of numerical integration, right? So the most naive approach to me is just doing Monte Carlo sampling. So there is a very popular method that was suggested in 2008 by Lechimi and Recht. It's called random Fourier features, and it was, well, basically one of the motivations for this work. So all they do here is really just look at this integral, consider it for shift invariant kernels, okay, and do Monte Carlo. That's the approximation. And it's very simple, right? It can be used for high dimensions, right? It's a very direct method. Okay, and you can think about that again in the terms of the feature maps as, well, you can write the whole integral as a near product of the feature map with itself, right? But in an infinite dimensional setting. But when you do this approximation, everything becoming finite. So you can think about that in this way. Okay, so this was the RFF methods, and what I want to do is something else. I want to use Gaussian quadrature in order to approximate this integral. So just a quick reminder, because I'm not sure everybody remember that. So in Gaussian quadrature, what you have is fixed weights and nodes, basically. And you have exactness for polynomials up to the degree of 2s minus 1 when you have s samples, basically. So I want to use a very specific rule, Gaussian rule, in order to do this integral approximation. I want to use Gauss-Legendre rule. And Gauss-Legendre rule just uses the uniform density function as a weight function. Okay, and the reason I want to use that is because, let's go back for a moment. I want to be able to approximate a really rich family of kernels. Okay, I don't want it just to be Gaussian, for example, or just to be kernels that are shift invariant. Any kernels that can be represented as this integral, I want to be able to represent them. So if I choose uniform weight and I use this density function as part of the integrand, then I can just apply it for any kernel that I want, basically, in this form. Okay. Okay, and maybe two more things to know here. That first, everything is fixed. Okay, so the nodes are fixed, the weights are fixed. You know it all from advanced. It's not like in Monte Carlo when you need to sample over and over again and produce your samples. So we know everything right from the start. And another thing I want you to pay attention here is that if I look, for example, in the 2D, in the 2D plot, you can see that you have more samples near the boundaries, which will be very useful for us. We'll explain it in just a few slides why. Okay, so how do we do it? How do we apply this Gauss-Legendre quadrature rule? So basically, I will show you that looking at the integral error approximation is the same as looking at the kernel approximation error. Okay, when you have some delta that you want to have as the error, right? And these are this z of theta. These are basically the vector of features. Okay, so I want to, of course, analyze this error using Gauss-Legendre quadrature and see how many nodes I need in this quadrature rule to have this error. So basically we have two steps here. So the first step, we take this integral and truncate it into symmetric intervals. Okay. The second stage, we take this truncated integral and approximate it with Gauss-Legendre. Okay. And the reason we do that is the following. So first, if you want to use Gauss-Legendre, we need to have some symmetric intervals, right? The second is that we use analysis of decay's properties for the density function P. Okay? So if you have, let's say, a very strong decay and you truncate it here, right, you don't lose much information from the boundaries, right? So we kind of assume that we have enough information when we truncate it. So the question is, which parameter U we need for this truncation? Okay, and you can see, of course, here in the example that, of course, for Gaussian kernel, this one has the most strongest decay among them all, right? But basically, the faster the density decays, the smaller is the interval we will need in order to have more of this information.
Excuse me. So if
What is F?
Yeah.
Yes, sorry. So just a notation for whatever in the integral, which is the features and the scaling parameters. Okay. So it was the phi that I had before. Just a simple notation. Okay. Okay, so first step, we do this truncation. And in the second step, we take this truncated integral and just apply Gauss quadrature, well, Gauss-Legendre quadrature to it. And also here, the analysis that we use in order to do the error analysis. So we consider Chebyshev expansions, and then when you write everything down according to the Chebyshev approximations, the faster your Chebyshev coefficients decay, again, the smaller is the number of samples that you need. By samples, I mean, of course, the nodes for the quadrature. Okay, so we have a really nice analysis here. I don't give the whole, the list of theorems and analyses in this talk, but basically, that's what we have. Okay, and maybe just another thing to mention is that what do we need to assume to have these coefficients decay? So basically, in the theory of Chebyshev approximations, most of the time you need to have some smoothness assumptions for the function or analytical assumptions. So maybe this is the weakness of our model, that we assume that everything here inside is analytic. And what we do is just consider a few classes of kernels and analyze each of them separately and see what we have. And for, at least for the most interesting cases that we consider, we do have this assumption of analytical. Okay, and maybe another thing to mention is that for most of the kernels, we have number of nodes that is polylogarithmic, okay, which is really great because, for example, in the Monte Carlo based approximation, these random Fourier features, there are many variations for the analyze they do there, and there are many improvements today, but basically you can reach to linear number according to the number of data points. Okay. Let's see how over with time. Yeah. Okay, so just regarding the decay properties, so for example, this some of the classes that we consider for the density decays. So the first one associated with Cauchy kernel, I think. The second one will be for the Matern kernel, and the third one will be for Gaussian kernel. Okay, as you can see here. And when we do this analysis, you can see that indeed for the case of the Gaussian kernel, which is the third one here, we obtain the smallest number of truncated parameter here. Okay, so this is again because this is the strongest decay you have. So there is a really strong connection between how smooth is your function and how small your truncation is. Okay, and yeah, and now what I want to do is connect everything to approximate the kernel matrix. Okay, so we have a really nice definition of spectral equivalence that says that, for example, K tilde is the approximate matrix kernel for K, right? Of course, it can be anything here. So this is the definition. And assuming that we have that spectral equivalence, we can obtain some nice property about the KL divergence between the two, well, actually, probabilities that you are trying to approximate. Okay? So basically what I want you to take from this maybe is that approximate the integral according to simple numerical analysis tool is the same as doing this KL divergence approximation for your kernel and covariance kernels. And what we do, okay, in this definition, we actually take this delta that I used before as the quadrature error to be 1 over n. Of course, it can be anything you want, right? But this is the definition we found to be, let's say, more efficient. It's not too small, it's not too big, it fits everything. And then you just split the errors between the part where we truncate the integral and the part where we do this quadrature rule. Okay, so in some of the time I still have, I just want to maybe show you some of the pros that I have when I approximate this kernel matrix. So basically, if I translate everything, take this integral representation and write it down as the kernel matrix, this is the approximation that I get. And this is a low rank approximation. So the same is the Monte Carlo based approximation. Also here we have something that it's low rank. So let's see what we have here. So, so Z is the N over S matrix, which composed from these features. Okay, this feature map sampled at the data points and the nodes of the quadrature rule. And W is a diagonal matrix. Okay, and it's very nice because basically all of your weights and hyperparameters are there. So this Z matrix does not contain anything about the hyperparameters. And this really makes our life easier when we come to solve the maximum likelihood part of this problem. Because then when you do all these nasty derivatives, you can just look at this diagonal matrix W and all your hyperparameters are there instead of just look at the whole matrix. Okay. So for example, for the hyperparameter learning, instead of doing it naively and use cubic number of computations, we, according to n, basically we have ns plus n to the third plus sd, and d is the dimension, of course. Yes?
Sorry, under what assumptions do you get the fact that only the diagonal matrix depends on that from?
That's the way we define it.
Sorry?
This is the way we define it. Sorry.
Oh, okay, I'm sorry.
Because I will write it very in the simplest way, right? But basically you have something like this, right? So, and this F is actually some inner product between these phi's, right? So we can factor that out into multiplication of Z and Z transpose, and in the middle you have everything of the weights. So maybe this is the trick here. It really accelerate the computations for the maximum likelihood.
So in the W of theta,
Yeah.
The right-hand side is just theta 0. Should the left-hand side W also be a function of theta 0?
Yes, so yeah, I think it will be too many slides. Let me try to find it. Yeah, okay. Okay. Yeah, I'm sorry. I have a lot of notations, but basically you can consider theta as your, set of all hyperparameters, and theta 0 is all of them except to the scaling parameter and the regulator, just to be because many of the times they're just, you know, running to someone else. So. Okay, so this is the approximation, which is low rank again, and yeah. And now when we are doing this hyperparameter learning phase, everything is much more efficient. So for example, if you want to look just at the first derivative according to the scaling parameter, you need to compute this whole thing again. But one thing that we can do, for example, is keep this z, compute it only once, and keep it through the whole process, because every time you update your hyperparameters, only this w changes, right? So there are many tricks that we can do here in order to save some computations.
So what was Z?
Yeah?
What was Z here?
Z?
Yes.
Okay. So Z is the matrix composed from the feature map when you have inside your dataset points and then quadrature nodes. Okay.
Thank you.
So for example, for the Gaussian kernel, it will be this exponent. Yeah.
Sorry, while we're at it, I really have a burning question. So,
Yeah.
when you introduce this matrix in the slide before, you talk about the spectral equivalence. Do you assume that this low-rank matrix is spectral equivalent, or will you show this later?
I assume, well, so yeah, it's a tricky question because in some sense I assume it, but it also happens naturally. Because the beauty is that when you translate that into the integral form, so it's actually the same. So the quadrature error is the same as having this spectral equivalence, basically. So maybe I should say that the quadrature error was the motivation to define this spectral equivalence.
So you mean you set up your quadrature such that you get spectral equivalence?
Exactly. And I know from, I knew from the beginning that it will be exactly the quadrature error, yes. Yes, so this for the hyperparameter learning. And then, of course, you want to do the training and prediction. So for that, we just need basically to, well, we saw it the whole 3 days that we are here, right? Just compute some multiplication between the kernel matrix and basically this alpha vector, which is the solution of the least square problem, okay, when you have this kernel matrix inside. But here I don't need to compute it directly if I use some matrix identities such as Woodbury, okay, and it's just a very long computation, but again, the thing is that instead of inverse, instead of having inverse of n times n matrix, I can have s times s inverse of matrix. So again, less computations. Okay. And the same goes for the prediction, of course. Okay, great. So again, the main motivation for this was the Monte Carlo-based approach, which is RFF. So if I want to compare between the two, let's just set up everything we need. So again, this method is only for shift invariant kernels, okay? Only for those you can represent as Fourier transform. So just to keep everything very simple, let's assume that all the hyperparameters are scaling parameters. Okay, so you have this L diagonal matrix. So for example, in the Gaussian kernel, you have the bandwidth parameter, right? And again, you have this kernel approximation. So now when I want to write down the matrix approximation according to this method, I don't have this diagonal in the middle, okay? So if you try to write it down explicitly, you will see that all the hyperparameters are inside this matrix Z, which is, okay, very similar to the previous Z that we had. But you cannot escape from having these hyperparameters inside here. So what does it mean? Okay, it means that now when I want to do this hyperparameter learning in my GP process, okay, I cannot escape from compute this matrix again and again in each iteration. So this is why this is a very simple and nice method in general, but it's not very applicable for GPs. Okay? And this is the table of comparisons according to the computations. So again, you can see that for training and prediction, both methods very similar, but the main, advantage of our method, of the Gauss-Legendre features, is in the hyperparameter learning time. Okay, so here, for example, we consider I to be the number of gradients computations that you have, okay, in each, in all of the iterations, and you can see it's much better. Okay, and yeah, so I focused on really the shifting variant kernels, but again, it can be anything, okay, any kernel that can be represented in an integral form. I think, yeah, I didn't put it here, but there is a paper actually that suggests that any kernel in general can be represented in this integral form. Maybe you will have more frequencies in the integral and not just one, but still. So I think this is very applicable. So another example that we can consider to show you just, you know, we don't only have shift invariant kernels, is consider the half-line and look at something that looks like Laplace transform. Okay? Yeah, and I think I have some, well, this should be this delta x tag as I showed before. I'm sorry about that. But again, if you can consider, for example, this reciprocal semi-group kernel, this is one example for such kernels that can be represented with Laplace transform. So this is another example. And you can do the all analysis that we did for symmetric intervals also here. Just do some linear transformation, right? Okay. So in the few minutes that I have left, I just want to show you a few examples, numerical examples. So how do we do that in practice? Okay, because we have so many types of parameters, right? So we have the hyperparameters, right, of the kernel, and we also have this u and s. So u again is the truncation parameter for the integral, and s is the number of nodes. And if you need to remember anything from my notation, it's just these two. So how do we do that in practice? Because basically they depend on each other, right? So what we do is search locally, okay, for the maximum likelihood part. We search locally for the hyperparameters, and we consider some finite intervals where we look at. Of course, we choose them smartly, but then we can consider, for example, these parameters u and s to be the ones that fit the worst case that can be. So for example, here you can take the largest value of the regularizar and consider that as the one that determines your u and s parameters, for example. Okay? So this is how, let's say, we guarantee that maybe we took, you know, a bit bigger interval than what we need, but we didn't lose anything. Okay, so here, for example, just to show you the log likelihood learning, we have a synthetic example, and you can see that, well, we have the black line is the exact Gaussian process learning without any approximation. In the red line, which is exactly on the black line, we have the Gauss-Legendre features, and the magenta line is, of course, the RFF method. Okay, so you can see that for any of these hyperparameters, for the Gaussian kernel, in this example, we have a nice learning. Okay, and this is the approximations. And what I also want to show is a few real data sets. So for example, here we have natural sound modeling. So of course we want to have the missing parts in our signal. So we use the Gaussian process. Okay, and this is a very large data set. Okay, one-dimensional, but still very large. And I focus here on the errors and the learning times in the graphs and not the uncertainty, but of course you can derive that as well. So here you can see in the right top plot, you can see all the methods compared to each other. And again, the red line, which is our method, is exactly on the method without any approximation, right? And you can see the real benefit here in the errors and the learning time graphs. So the thing is that once we reach to the theoretical number of nodes that we need according to the analysis that we do, that's it. I mean, the error just stabilizes there. But for the magenta line, the RFF method, okay, you see it's still jumping around. And it's not even close to our method. And maybe the biggest benefit here is the learning times between the methods when you do this hyperparameter learning. Okay, so here we have another example for Google Daily Highstock. Okay, so again, it's a one-dimensional example, but just to visualize everything. So everything looks pretty similar to what I just explained. And maybe the last interesting example is for spatial dataset, okay, which is basically the motivation for this work. You can see here on the left bottom plot that the magenta line for the RFF method just stopped. Okay, so this is a really funny story. When I was a PhD student, of course I could pay and run everything on Google servers or anything, but I think it's proved the point when memory was out. And the method just, stopped here and the number of these nodes. But the Gauss-Legendre method just continues, and you can still see that the error stabilized. And same for the learning time. Yeah, so maybe I should just say that the whole analysis is for multidimensional data sets, but it's mostly applicable for low-dimensional data sets because the motivation was spatial data sets, basically. And we do have the problem, of course, of the dimensionality because we have this dependence of the dimension, and we have some ideas, of course, how to generalize everything for high dimensions, but that's what we have at the moment. And if you're interested, this is the paper, and if you have any questions or want to discuss, I will be happy to.
Thank you, Cass. Are there any questions? Let's start with you.
Do I get correctly that if U and S go to infinity, then it becomes exact?
What become exact?
The approximation?
But what goes to infinity? Oh, you mean the number of nodes?
Yeah.
Yes, basically, yes.
Yeah. And then because in the comparison with Fourier features, you would have a similar thing, right? If you have enough features, then I suppose both lines would be the black line.
Yes.
Is that comparison then for sort of a fixed number of features, or?
What do you mean by? Yeah, I mean you have some theoretical number that you consider, right?
Right.
So, yeah, actually that's a good question. I don't remember at the moment what benchmark I used to determine the S of the random Fourier features, but one of the existing, you know, analysis for that. But again, it's most of them are linear according to the number of data set points. So.
And maybe one question on the marginal likelihood estimates that you get. They are, I suppose they have some. Can you share anything about the sort of error compared to the actual marginal likelihood? Is there anything known?
Yeah, so that's a good point. I mean, we did not use the error comparisons for the likelihood itself, but it's a good point. Maybe it's good to do this. We stayed focused on, you know, just showing the computations that are more efficient. But yeah, basically you are right.
Will work.
You in front, did you have a question?
Yeah, so you had mentioned at the very end that there's this dependence on the dimensionality of the data, which is exponential, I think was the correct result that you showed. Right?
Yeah, let me go back to that. This one.
Yes.
Yeah.
So it seems like, am I correct in assuming that this comes from the fact that you use quadrature, and quadrature is just hard in higher dimensions in general, versus Monte Carlo is the tool that you would...
Nobody does quadrature in higher dimensions, basically. Yes.
So basically you would expect that for higher dimensions, RFF would then again work better. Right?
I guess so, yes. So again, this whole thing is good for lower dimensionals.
Yeah.
And we do have some ideas of how to do this in higher dimensions. So for example, if I go back to this grid plot, so this is a very dense grid, right? So one thing that you could do is use sparse grids, if anyone is familiar with that. But basically it's just a some approach to, you know, choose some of the nodes and not all of them, and have a less dense grid in order to do this in higher dimensions, basically. So this is, for example, one idea to do that. But yes, but the more dimensions you have, I guess the random Fourier features will be better. Yeah.
But in turn, if there's a quadrature method that works for a certain class of function in higher dimension, this should translate to this, right?
Yes. And again, I think it's also good for lower dimensions, but also I think the benefit is that we do not assume a very specific family of kernels. So, for example, you cannot use this RFF method for you know, the semi-group kernels that are, you know, they use the Laplace transform, for example. Yeah.
Thank you.
Yeah, thanks for interesting talk. So, as you would know, like this, your course has a paper using Clash Monte Carlo. So there are other works using deterministic quadrature rules for this kind of approximation. And can you compare with these approaches? What is the advantage in your?
So in the paper, there are a few versions of these random Fourier features. There are a few versions to that method, which is, I just showed the vanilla one here. And there are many other low-rank approximations, or, you know, that you can compare to. But I wanted something that is with this integral form specifically that I can compare, you know, in terms of properties of my approximation. But yeah, basically you can compare it.
Yeah, I wanted actually to ask a question along those lines. Let's say I take a step back and I interpret this result from the integral as, okay, you are able to derive an expression that is low rank plus some diagonal, or no?
Diagonal? Why
from the
diagonal?
regularizer. No?
Why diagonal?
Sorry, you had this slide after the spectral equivalence.
You mean this with the diagonal matrix in the middle?
The I is not a diagonal matrix.
So the Z's are low rank and the I is the diagonal matrix, so low rank plus the diagonal.
Yeah, the Z is the low rank matrix.
Yeah, and
It
I
is
is
the-
identity matrix.
Where?
No.
Oh, yeah, of course. Yeah.
All right, so low rank plus diagonal.
Yeah.
Yes.
This is low rank.
Let's say I take this as a statement that most kernels have this structure,
The integral structure. Yeah. Maybe
but this is the spectral equivalence holds for this now.
for this approximation. So this is the spectral equivalence, basically, and it's the same as doing the quadrature error. It's the same. If you write down this inequality in terms of the integral, that's what you get.
All right. I'm not sure I can interpret this, but I was wondering if you could just assume that this structure is there and bypass the integral and just find some measurement paradigm that
Yes.
assumes low rank plus diagonal and do quick measurements that way.
Oh, okay. So you suggest something different, right? I mean, take low rank
but
plus
take
diagonal.
this as a theoretical
Yes.
motivation for that.
Yes, so there are many papers that suggest similar structure. Yeah, but I think the problem with this type of method, and this is a different type of methods that are data dependent. So for most of them, of course, what you may suggest is different, but what exists is that you define this low rank approximation, maybe according to the data you have, and then in each iteration, you need to sample more and more from the data. So it really depends on what you want to do. If you
Right, the
okay
advantage
with
of this is that it exposes the parameters in the diagonal, which makes it much faster.
yes, that's the benefit basically. Yes.
Okay, if there's no further questions, then let's thank